Hello, this is Concrete Path. Let's go for the problems for effective stress calculations and the effect of capillarity. Let's go for number one. So we are given that a soil profile is given. There's a 3.5 meter layer of sand. After that, there is 3 meter layer of clay, and after that, we have 3.5 meter layer of gravel. Okay, this is your soil profile. So this is a cross section, I would say, of the soil profile. Let's say that this is ground level. This is the ground level we have. This is the ground level, and water table is somewhere here. So we are getting the water table here. After completing the level of sand, there we have the clay layer, and at the top of the clay layer we are having water table. This is your groundwater table. Groundwater table is there. So density of those unit widths, I would say density of those soils is given. Let's say this is your 1650 kgs per meter cube. This one is your 1.95 tons per meter cube. This one is your 1925 kgs per meter cube. Okay, and there's also a surcharge applied. Surcharge is also applied. Value of Q equals to 58.86 kilonewton per meter square at the ground level. So this is applied. Surcharge is applied at the ground level. Let's think of a building. Let's say that building is there. So that's your surcharge on that soil profile. 58.86 kilonewton per meter square. Now we need to have the variation of that effective stress. Get the effective stress variation along the profile. Calculate the effective stress profile. That's let's say that this is point A, point B, point C, point D. So we need to calculate effective stress at A, B, C, D. Let's go for that. I would say your effective stress is actually that's the difference between total stress minus pore water pressure. So if we try to calculate first that what is the total stress, then after that we can say what is the pore water pressure. Finally, I will write the difference of the two would give me effective stress at that particular point. Let's take the section A. I would say what is the stress at the section A. So if I take the section A, at section A, what is the weight above? Can you tell me what is the weight above? So actually the total stress is actually weight above by area cross section. So here we would write that total stress at the point A is actually equals to Q, because there is no any that soil layer above that ground level. Above the ground level there is no soil layer. So that means your stress because of the soil is not there, but we are only having that surcharge. External stress applied, that is surcharge, so that's equals to Q. So I would write that total stress at the point A is actually 58.86 kilonewton per meter square. And I would say that this stress is because that this load is applied, and we are calculating after a very long time. After a very long time. After a very long time. So this surcharge is already placed there on the soil from a very long time. So this is already placed at that site. So that means your total stress is actually 58.86 at the section A. What is the pore water pressure there? What is the pore water pressure at that point? I would say there is no water at that point A. There is no water. So that means there is no water in the pores. So no pore water pressure. What is then the effective stress at the point A? Is that difference of the two? So that's actually 58.86 minus 0. That's 58.86. That's equals to total stress, and that is equals to surcharge. Now let's go for the section B. Section B or point B. I would say what is the total stress at that point A, point B. So that's actually what is the total stress above that. So that's equals to Q plus your stress because of the dry soil. So I would write gamma D into 3.5. Gamma dry into 3.5. So your Q equals to 58.86 kilonewton per meter square, and your gamma dry for your soil is actually 1650 kgs per meter cube, and into 9.81 meter per second square into that 3.5 meters into 3.5 meters, and that would be some value. That would be some value around 115.5 kilonewton per meter square. And what is the pore water pressure at the section B? What is the pore water pressure at the section B? I would say above the point B. If you try to keep at this point B, if you try to have a, what you call as that piezometer, if you insert a piezometer here, what is the level we get in the piezometer? I would say the piezometer would have a level of up to the point of ground level. So there is a rise of liquid in the piezometer equals to the level of the groundwater table difference from your point. Groundwater table elevation difference from your point concerned, from your point. So your H is equals to your elevation difference from the groundwater table with respect to your point of observation. So your point is actually on the groundwater table itself. So your H would be zero. So your pore water pressure would be zero. So pore water pressure is zero at that point. Pore water pressure is zero. So effective stress would be 115.5 minus zero. So that's your effective stress, kilonewton per meter square. Let's go for section C. Let's go for section C. Let's go for the section C. So I would say at the section C, what is the total stress? Total stress would be total stress above 8. That's total weight divided by area of the cross section above 8. So that's because of Q, because of gamma D into 3.5. Plus we have one more thing, that's saturated sand. So this is saturated, that what you call as saturated unit weight. Saturated unit weight is given to you as 1.95 tons per meter cube for the clay. So I would say that's your 1.95 tons per meter cube into 9.81 meter per second square into one more thing is there, that is 3.3 meters. Yeah, 3 meters because of clay layer. This was because of sand, and this is because of surcharge. So we have the final value, that is 58.86 plus gamma dry was initially that we already have calculated the total value of the first two terms. We have already calculated this part. We have already calculated. We can write that directly. That was 115.5, 115.5, 115.5 plus what is this value? We can solve that, and that finally would be equals to uh, finally comes out to be equals to that total stress at that point C is equals to 20, yeah, 172.90 kilonewton per meter square. And the pore water pressure at the point C would be actually the if you try to insert the piezometer at this level, you would get the level up to you would have the rise of water up to the level of groundwater table. So this would be the rise of water. So that's actually your pore water pressure is actually gamma W into that height of 3 meters. That is the elevation difference between that point and the groundwater table. So that's 3 gamma W. So that's 3 gamma W. 3 gamma W. So that's your pore water pressure. That's 29.43 kilonewton per meter square. And from those two, we can get the effective stress at the point C. That is actually 172.90 minus 29.43. That's a value of 143.47 kilonewton per meter square. Now, finally, is there that total stress at the point D? Total stress at the point D. So we need to now calculate total stress at the point D. So total stress at the point D, that would be the weight above that soil, weight above that point D, and divided by the area of the cross section. And so the stress is contributed by Q plus gamma dry of that sand for the height of 3.5 meters, plus one more stress because of the clay layer. So I would write 1.95 tons per meter cube. We can write that in this way. That's your gamma sat for the clay, for the clay into that meter 3 meters plus after that we have one more saturated soil of gravel. So I would write gamma sat of the gravel into 3.5 meters. That is the total stress. So we need, I would say first three terms we have calculated. These three terms we have already calculated. That was actually total stress of the sea. Total stress at the point C, 172.90. 172.90. So that's 172.90 plus that gamma sat of that third one. So plus, we can write it in this way, 1.1925 kgs per meter cube into 9.81 meter per second square into that 3.5 meters. And this value finally would be total stress at the D. Total stress at the D. So that would be 238.99 kilonewton per meter square. And after that, we would say, what is the pore water pressure at that point? Pore water pressure at that point D. So you would say, let's insert the piezometer at the point D. Let's insert the piezometer at the point B. You would see what is the rise of the water? Up to what point? I would say the rise of the water would be up to the level of groundwater table. So elevation difference is actually how much? 3 plus 3.5. That is 6.5, 6.5 gamma W. 6.5 gamma W. That's your pore water pressure at that point. That's 63.675 kilonewton per meter square. So finally, your effective stress at the point D would be sigma minus U. That's a difference of the two. That's 175.22 kilonewton per meter square. So we got those values at the critical locations. Now, if I try to have a diagram for that, that is the stress diagram representation, stress distribution diagram. Stress distribution diagram. Let's go for the stress distribution diagram. Let's go for that stress distribution diagram. Let's try to write that. Let's try to draw those stress diagrams. I would say this is your initial reference line. There is one more. Let's go for the total stress. Let's try to draw the stress. We would call it this one as stress distribution diagrams. Distribution diagrams. Stress distribution diagrams. Okay. So let's go for the first case, that when what call as we are calculating for the total stress diagram. When what is the I would say, what is the stress at the point A? What is the total stress at the point A? If this is your point A, let's try to have those lines. Let's try to have those lines also. Let's say that this is your line number 1. This is your line number 2. One more is there, and final is there here. Okay. What is the stress we got at the point A? Total stress. That was 58.86. 58.8. Let's say that we got the 58.86. This is your 58.86. And what is the stress we got? What is the stress we got at point B? Stress at point B. So that's your how much? 115.5. 115.5. Let's say that 115.5 is somewhere here. Let's say this is your 11.5, 115.5. So I would have that linear variation. I would have the linear variation of that, because you can see that equation. You can see the equation that this is your y equals to mx plus c. Your function of that stress is a function of that depth. As you increase that depth height, so that's the linear variation. Linear variation of that elevation. Linear variation of that elevation. So that's a linear variation. That final is the linear variation. And what is the total stress at the point C? Is that 172.90? So 172.90 is somewhere here. 172.90. So after that we would have one more linear variation. But the slopes would differ because that your m is varying, because your mx plus c, I would say your m is varying. Your gamma d is varying. In the third case, you would see your gamma sat was there. Your gamma sat was there. That is varying, because up to this part this is fixed now. This part is fixed now. Only the gamma sat is varying now. Gamma sat is their m. This is different value, and your h is now varying for the clay layer, and your m has been different from as compared to dry gamma dry. So this was having some slope of m1, and we're having different slope m2. So that's where we are having different slope here. So finally, what is the total stress at the point D? What is the total stress at the point D? Total stress at the point D, that's 238.99. 238.99. Let's have that one also. 238.99 somewhere here. Let's say this is 238.99. So finally, let's join that also, and this is your final total stress diagram. Total stress diagram. So we can also say that your total weight above any cross section becomes a surcharge for the soil below. So if we try to say that this acts as a surcharge for all the soil below it, acts as a surcharge, and when we have this much amount of total stress at this section, and this total stress acts as a surcharge for all that soil below that, and similarly this total stress at this section C, this acts as a surcharge for your soil D. This acts as a surcharge for your soil D, such that you have a constant stress for all those fibers, and only that increase is because of this part is increased because of gamma sat in the gravel and their height that elevation difference of 3.5. So that's your total stress. We got that. Now we need to get now pore water pressure. We need to get now pore water pressure. We need to now get pore water pressure. Pore water pressure. Pore water pressure. We need to get pore water pressure. So I would say, what is the pore water pressure initially? What is the pore water pressure at point A? So that was 0. Pore water pressure is 0 because there is no water, and pore water pressure is also 0 at point B. Pore water pressure is also at point B equals to 0. So I would say up to the up to the value of ground level, up to the value of groundwater table, your pore water pressure is actually 0. Your pore water pressure is 0. So here we have pore water pressure, that is 0. After that, there would be linear increase as per the hydrostatic condition. So we would have increase of that unit weight, increase of that pressure with the increase in elevation. So the linear variation would be there for your pore water pressure, linear variation, and this would be gamma W into total height of 6.5. That is the sum of the height of the clay layer plus gravel layer, 6.5 into that 9.81. So total stress was that how much was the final value of stress? 6.5 into 9.81, 63.67, 63.765. So that's your stress pore water pressure diagram. And what is the value of pore water pressure at this point? At the section C, your pore water pressure is 3 times 9.81. So that is 3 gamma W. That is this much amount of that height, 3.3 gamma W. So that's your 29.543. So this stress is 29.43. Now let's go for the total effective stress diagram. Let's talk about the effective stress diagram now. Effective stress diagram. Okay. I would say your effective stress diagram is actually sigma minus u. So at this section, we don't have any, we have zero pore water pressure, but we have 58.86 of that total stress. So this would be 58.86. After that, we have this much 115 at this location, so we would be having 115.5 because your pore water pressure is not there. Now at this critical location, at the section C, what is the total effective stress? That is actually 172.90 minus 29.43. So some value we will get here. That's coming out to be equals to, that would be equals to, what was the total effective stress at the point C? So that's 143.47. We can see that difference of the two, 143.47. So that's 143.47. After that, we would say, what is the total pore water pressure here? What is the pressure here? Total stress, that is 238.99. 238.99 minus what is this value? 63.765. So that would be effective stress at the point D. Effective stress at the point B, that's actually how much? 175.22. 175.22. So final value of 172.5, some value 172.55. So this is your effective stress distribution diagram. So that was all about that problem. Okay. Let's go for number two. Let's go for number two. Let's go for number two. So we are having that. We are having 8 meter layer of sand. 8 meter layer of sand is there. And after that we have 6 meter layer of clay. 6 meter layer of clay. Let's say that the clay layer is somewhere here. This is your clay layer, and 6 meter. I would say this is your 6 meters. And from the top, I would say this is your 8 meters. And the character of that sand is given that we have specific gravity of those solids 2.65, void ratio of 0.85, effective size d10 equals to 0.14 millimeters. Your value of C is equals to 0.5 centimeters square. And we also have that water table is somewhere. So we are having water table also. We are having water table also in the sand. So if I say that this is 8 meters, if I say that this is 8 meters, and uh, at 6 meters from the ground level, at 6 meters from the ground level, we are having water table. So somewhere here we are having water table also. So this is water table in the sand layer, and this one is your 2 meter water table in the sand layer. 2 meter. This is your groundwater table. Okay. Now, what about the clay? What about the specifications of clay? We have the G for the clay solids, 2.75 water content for the soil, 22%. And this would be saturated. This is also saturated. Can we say that? This is saturated clay soil, saturated soil, because we are having groundwater table here. And this one would be some bulk condition based on the given dimension, based on the given properties of that soil. So as the data is given, is there any possibility of capillary rise? Is there any possibility of capillary rise? Let's try to have that equation of capillary rise. We have the equation that capillary rise is equals to C by ED10. C by ED10. So this is your in centimeters. This value it's given to you as 0.5 centimeters square, and divided by the value of void ratio 0.85, and into that D10. D10 is in millimeters, so we have to keep that in millimeters. So what's the value, total value in centimeters, capillary rise? Capillary rise, that is 42.02 centimeters. And if I try to keep that in meters, what is that value? So we can say that this is your 0.42 meters. So there is a capillary rise of 0.42 meters. That means above the groundwater table, we will be having that capillary rise up to the height of 0.42. So that means up to somewhere here we're having capillary zone. So this is your 0.42 meters. 0.42 meters. Here we have soil that is saturated. We would say that the soil is saturated here because of capillary zone. Capillary zone. So we need to now calculate finally. We need to now calculate finally that those diagrams: stress, pore water, and effective stress. Total stress, pore water pressure, effective stress at those critical locations. At critical locations. Okay. Let's try to get those. Now we have already calculated all that stuff. Now we will be going for direct what you call as diagrams. We'll be going for the direct calculations for your stress diagrams, because that's all stuff we know how to get that. We'll be going in that same way that we don't calculate all that stuff. We'll be getting for the diagrams. Okay. Now, for getting the stress at any point, we need to calculate what is the unit weights of the soils. What is the unit weight of the soils? So once we got that, how much rise is there? Let's remove this part. Let's remove this part. Now I would say what is the what you call as what is the unit weight of these soils? What is the unit weight of these soils? So I would say for the first part, I can say this is your soil that is dry. I can say this is your dry soil. So for that, I would say gamma dry is equals to G gamma W in terms of 9.81. I can calculate G gamma W by 1 plus E. That's your gamma dry. And what about this saturated sand? Saturated sand. So for the saturated sand, I can solve that this is your gamma sat. This part is also saturated, this part is also saturated. But the difference here is this is saturated because of capillary zone, this is because of gravitational water, because of gravitational water table, because of gravitational forces. So that both of these are sand and what you call as saturated, sand saturated. Degree of saturation equals to 1. So we have the equation gamma sat equals to G plus SE by 1 plus E into gamma W. So that's also equals to G1 plus W by 1 plus E into gamma W. So we can solve that, we can simplify that, and we can substitute the values. Let's say G is your 2.65 into 1 plus water content, that's 0.85, and divided by 1 plus E, 0.85. Yeah, water content is not given to us, so I can substitute this first equation. I can substitute the first equation. I can write G plus SE. Yeah, see, in this case, is the degree of saturation given? I think degree of saturation is given because we are talking about the saturation. So I would write that G plus E. So G plus E, here the degree of saturation equals to 1. So I had to substitute the value of G plus E by 1 plus E into 9.81. So that is your gamma sat for your sand. What about for the clay? So this is also saturated. This is also saturated because of gravitational water. And the gamma sat for this one, for the clay gamma sat is equals to G plus E. Yeah, in this case your E is not given, so I would write SE equals to WG. So your E can be replaced equals to WG. So I would write finally G1 plus W, 1 plus W by 1 plus WG. So we have that equation into 9.81. We'll be using that second part of the equation. Your value of E can be replaced by WG by S, but your S is 1, so your E becomes WG. Okay, so finally we can have those values. We can get the values. Let's say that gamma dry is equals to, gamma dry is there. That's, we have calculated those in terms of, we have substituted the value of gamma W as 1 gram per cc, or 1 ton per meter cube. We can substitute in that way also. So let's say that we are keeping gamma dry in terms of final value as 1.89 ton per meter cube, and gamma sat is equals to, yeah, gamma dry is 1.43. Gamma dry is 1.43. Gamma sat for the sand 1.89 tons per meter cube, and gamma sat for the gamma sat for the clay 2.09 tons per meter cube. So finally, I would say, let's remove all that stuff now. Let's remove all that stuff. So let's remove this stuff now. Let's try to only visualize our important data that is needed for our calculations. That's needed for our calculations. So finally, we are left with this part. 2.09 is there, 1.89 is there, and 1.43 is there. Now we can get the solution finally. Now we can draw the diagrams. Let's try to get the diagrams. I would say let's have those connections between those. Let's say these are your connections for the diagrams. Go for the first one, that is total stress. So this is your total stress distribution diagram, sigma. And I would say, is there any surcharge at the top? At the ground level, is there any surcharge? I would say no surcharge is there, so your stress would be 0 at that point. After that, because there is no weight above, so stress is 0, total stress. And what about the stress at this location? Can you tell me what is the value of this height? What is the value of this height? What is the value of this height? Is that 8 minus 2 meters minus 0.42 meters? Can we say that? Total height of the sand layer is 8 meters. And when you subtract 2 meters minus one more is there, 0.42, because of capillary zone. So finally you are left with that. How much is that? 5.58. This is your 5.58 meters. So I would say the stress at this location would be that 5.58 into your unit weight of 1.43, that is dry unit weight. dry unit weight. So this is equals to gamma dry into 5.58 meters. So the stress would be some value of stress is there. So I would say that value is coming to be equals to, so that value is 7.98 in terms of tons per meter square, 7.98 in terms of tons per meter square, 7.98. And after that, I would say this is going to remain constant for all other soils below that. That's acting as a surcharge now. That would be acting as a surcharge now. That would be acting as a surcharge now. Okay. After that, we have the saturated what you call as saturated capillary zone. So in that we have 1.89. So 1.89. So I would write final value of 7.98 plus 1.89 gamma sat into height of that 0.42, into that height of 0.42. So this is the total stress at this location. Finally, this is coming to be equals to that uh, 8.77. So let's say this is your 8.77. This is your value of 8.77. After that, we are having 2 meter saturated sand. 2 meter saturated sand is there, and with that saturated gamma of 1.89. So once we got the value of 8.77, once I got the value of 8.77, I can finally write plus gamma sat into 2 meters, gamma sat for the sand into 2 meters, such that final value is coming out to be equals to 12.55 at this location. 12.55. So I would have that linear variation here. After that, one more linear variation, but the slopes would be different. Slopes are differing because your unit weight is differing. After that, I would say what is the stress at the final point here at this location. I would say at this location your stress is actually total stress 12.55 plus gamma sat for the clay, into that 6 meter of the clay, 6 meter of the clay. So final value would be final value is 25.09, 25.09. So here we have 25.09 tons per meter square. This is your stress total stress distribution diagram. So we can get these values actually. If we try to substitute those values, let's say for the first case we are substituting 5.58 into 1.43, 5.58 into 1.43, that's your value of 7.98 tons per meter square. And in the second case, that is your 7.98 plus 1.89 plus 0.42, that's your value of 8.77. After that, in the third case, that's your gamma sat was your 1.89. 1.89 into 2, that's final value of 12.55. And similarly for the final one, that's your 12.55 plus gamma sat for the clay is 2.09 into that 6. Finally, it's 25.09 tons per meter square. Tons per meter square. So your tons is actually, your ton is actually, 1 ton is actually that 1000 kgs, 1000 kgs, and your one kilonewton is actually 100. Your 1000 newtons. Your newton is actually kgs meter, kgs per meter, kg meter per second square. So that means we have to multiply here that value of g, 9.81, 9.81 meter per second square. So you can see all that stuff. We would go for n number of problems and you can understand what's happening here. Okay. So we got that total stress distribution diagram. Let's go for the pore water pressure diagram. Let's go for the pore water pressure diagram now. Pore water pressure diagram. Pore water pressure diagram now. Let's go for the U value. So I would say for the dry part of the sand, for the dry part of the sand, your pore water pressure is not there. So your zero pore water pressure is there up to the level of groundwater table. Can we say that? Should we say up to the level of groundwater table we have pore water pressure is zero, or we have to say up to this value we're having zero, then after that there might be some value of pore water pressure? What do you think? Because we have capillarity effect and there would be effect of capillarity, so pore water pressure is going to be different from as compared to the gravitational force only. If there was only gravitational force, if there was only gravitational force, then it would become, it would have been that, let's say that there was only gravitational force, let's say that there was no saturated soil, because of capillary zone. So your what you call as pore water pressure distribution diagram would have been 0 up to this point. After that, it would be a linear variation from the groundwater table. From the groundwater table, it would be a linear variation. But because we have saturated what you call as saturated zone because of capillary effect, I would say in this part, in this capillary zone, we have negative pore water pressure. We have negative pore water pressure. Do you know that? We have negative pore water pressure in this zone. So this one is your positive hydrostatic pore water pressure, and above that groundwater table, we are having negative pore water pressure, and zero pore water pressure at the what you call as groundwater table. So because if you keep that piezometer here, you would get a reading that's equals to zero. Zero height rise is equals to zero. So that's your effect of that what you call as capillarity effect. Let's go for the value of u. So I would say your water table is here, but your capillary zone, this is your capillary zone. So in that we would be having negative pore water pressure. So in the capillary zone we are having negative pore water pressure. This part is negative, and zero value is there at the groundwater table. So this value is equals to gamma W into height of 0.42, and this would be equals to 9.81 into, yeah, in terms of gamma W equals to 1 ton per meter cube. So this would be 0.42 tons per meter cube. 0.42 tons per meter cube. We can say this is your negative value, 0.42 tons per meter cube, tons per meter square. 0.42 tons per meter square. Okay. After that, there is zero at the groundwater table. After that, it would increase as a function of elevation, as a function of that height or elevation. So finally, it would be here. It would be some gamma W into height h, where your total height of h is equals to initial value. This was 6 meters, and groundwater table is there here at 2 meters from let's say this is your 2 meters. Finally, h is equals to 8 meters. H equals to 8 meters. So this would be actually 8 tons. So final value is equals to 8 tons per meter square. So this would be 8 tons per meter square. Final value. And this would be 2 tons per meter square. And if I try to have that final effective stress diagram now, so that is the difference of the two. So the zero at the start, and let's say that just before that capillary zone, let's talk about this location. At that point, we had to write 7.98 sigma minus u, 7.98 minus, just before, just above that level, what is the stress, what is the pore water pressure, can you tell me? Here we have 7.98. At that location, what is the pore water pressure? Is that zero? Is that zero? Just above that level, so stress at that location is zero. So I would write finally your effective stress is the difference of the two, 7.98 final value, 7.98. Now let's go inside. We are going to cut the section just after that. At that location, we are having 7.98 as the effective stress. We are having effective stress of 7.98. Then we have to subtract the pore water pressure. So at that level, pore water pressure is minus 0.42. Minus 0.42. So final value would be increasing by this amount, such that your total stress increase, your effective stress increase. So final value is here equals to 8.04. 8.04. Is it 8.04? 8.04. If sum of the two, 7.98 plus, I think it should be more. So how much is that? Let me check. 7.98 plus 0.42. That is 8.4. Yeah, it should be 8.4, I think. It should be 8.4. Let's say that this is 8.4. Let's say that this is 8.4. Let's say that this is 8.40. And after that, I would say at this location, your total stress is 8.7. Then you have to subtract that 0. So final value of 8.7. 8.77. After that, at this location, we have 12.55 minus 2. 12.55 minus 2, what is that? 11 point, is that 10.55? So there's some value 10.55. After that, we have 25.09 minus 8. How much is that? 16, 15, 18, 18.09, 17.09, 17.09. So some value of 17.09. So 17.09. So this is your effective stress distribution diagram. Okay, 17.09. So that was all about that problem. That was all about that problem. Let's go for the third one. Let's go for the third one. Then this one is very crucial for all understanding all those concepts we have for your effective stress and capillarity. Yeah, this is very important problem. This is very final. I would say this is very important problem of that concept. Let's go. Let's go. We are having few cases of the problem, and we are going to take one by one. We have three parts of the problem, and we're going to take one by one. Let's go number one. Let's go for the number one. We have this problem number three, and case number one is there. Initial case. Initial case is there. That's we have a 4 meter clay 4 meter clay layer is there, and it's overlain by 5 meter sand layer. You would see these terms, that's overlain, underlain is also there, underlain. So for this case we are having overlain. So that means you are having 4 meter clay. That means you are having 4 meter clay. You are having 4 meter clay, and it's above that layer we're having 5 meter sand layer. 5 meter sand layer is there. So this is your ground level. Let's say this is your ground level, and this is your 4 meter clay. And what is the property? What are the properties of your soil? So we are having a groundwater table somewhere. So this is your groundwater table. Groundwater table. That means this was your 2 meter, and this one is your 3 meters. 2 meter, 3 meter. In the sand layer we have what you call as groundwater table. And what about that top? So above that soil we would be saying your soil is dry, and below that we are having soil is saturated, and below that soil is saturated clay. Saturated clay, saturated sand, dry sand. So gamma bulk for the sand, I can write gamma dry or gamma bulk. So it doesn't matter. Let's say that is bulk unit weight is given as 17 kilonewton per meter cube. We can also think it of a gamma dry also. Let's say that this is bulk water, what you say bulk unit weight. And after that there's gamma sat for your sand is equals to 20, and gamma sat for the clay, that is equals to 19 kilonewton per meter cube. So this is the stuff we need. Now we need to draw those diagrams. We need to draw those diagrams. We need to plot those diagrams. Let's say that we're having few lines here. Reference points, reference lines. These are your reference lines. These are your reference lines. Okay. These are your reference lines. Let's have the number one. Let's go for the number one. That's total stress. Total stress diagram. I would say at the top, what is it stress? Zero, because no weight above that, no weight above that level. After that there is a linear increase of 17 into 3. So at this location we are having 17 into 3, that is 51. 51. We would say that 17 into 3, gamma bulk into 3. After that there is what you call as we have the saturated weight. So I would say this would be now acting as a surcharge for all soil below that. This would be acting as a surcharge, that is 51 kilonewton per meter square surcharge for entire what you call as soil below that level. After that there is what you call as there is gamma sat. There is gamma sat into 2. So we can write here we have this value of 51. So what is the increase now? What is the increase now? So this increase is actually what? This is actually 20 into 2. That is 40. So final value would be equals to 51 plus 40, that is 91. 51 plus 40. So this part was your 51, and this one is your 40. So final value of 91. Can we say that? And once this one has been achieved, that this would be now acting as a surcharge for your clay layer below that. So 91 kilonewton per meter square acting as a surcharge for the clay layer below that. So finally there would be again increase of that stress, total stress, such that we are having once more that increase of that stress, final value of that. This is your value of 19 into 4 meters. 19 gamma sat into 4 meters. So final value would be such that, so final value of that total stress at the bottom of the clay layer would be 91 plus 19 into 4. That is 167 kilonewton per meter square. Okay, is that easy? That it's a linear function of that depth. Linear function of that depth. We have to see, just multiply that length. What is the height elevation difference between the 2 points, and join by its straight line. It's easy. After that, let's go for the pore water pressure. Pore water pressure distribution diagram. So I would say there is no effect of, in the initial case number 1, we don't have effect of saturation, what you call as capillary zone. We don't have effect of capillary effect. We don't have capillary effect. So this is your water table. Above that there is no water, so I would say your bulk, I would say your pore water pressure is 0. Pore water pressure is 0 up to this level of groundwater table. Then you place piezometer somewhere here, you would get a level of water up to the level of groundwater table. So I would say your pressure distribution would be now linear variation of that, what you call as linear variation. So final value here would be total depth. What is the total depth here? Is that 2 plus 4, that is 6 meters. So we can write 6 into gamma w. 6 into gamma w. So what is that equals to? Yeah, we can substitute the value of gamma w as 9.81. Yeah, 10. Let's substitute the value of gamma w as 10 kilonewton per meter cube. Gamma w as 10. So finally I can write this one as 60. So final value is 60 kilonewton per meter square. And what about the value here? Is that 2 into 20? Is that 2 into 10? That's 20. Because we have 2 into gamma w at this location, at this section. 2 into gamma w. And finally, let's go for that, what you call as effective stress. Effective stress, sigma dash, sigma bar. So that's actually difference of the two. Difference of the two. Difference of the two. So here we have 0. After that we have 51. 51 is 0. 51 minus 0, that's 51. After that we are having that, we are having what you call as 91 minus 20, that is 71. 71 is somewhere here. Let's have a different slope. Let's say that the slope here is different. 71 is there. After that we would say your 167 minus 60 is their final value. So difference of the two, that's 107. So total effective stress at the bottom of the clay layer is 107 kilonewton per meter square. 107 kilonewton per meter square. Is that easy? Is that easy? Now this was the first part of the problem. This was the first part of the problem. This was the first part of the problem. Now second part, let's go for the second case. Let's go for the second case. So second case of the problem is that your capillary zone has developed up to 1 meter above groundwater table. So capillary zone has developed above groundwater table by how much elevation? How much height? 1 meters. 1 meter. So let's go for the diagram now. Let's draw the diagram for that. We have 5 meter sand, 4 meter clay. 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 And where was the groundwater table initially? Groundwater table is 2 meters from the clay layer above. So this is your clay layer somewhere. That 4 meter, 5 meter. This is 4 meter. This is 5 meters, and 2 meters is somewhere here. And we have this water table, and we have one more thing, that's capillary zone is 1 meter above the groundwater table. So we have capillary zone. So a capillary zone has been developed finally. So this was your sand, and this was clay. Sand and clay. Sand, clay. Okay, 3 meters. So finally, I would say this is your 1 meter capillary zone, C zone, capillary zone, and this was your groundwater table initially at the initial location, and this was 2 meters. And I would say this is your gamma sat because of groundwater table. Okay, this was your gamma sat in the clay, 4 meter, 4 meter clay, 4 meter clay, 5 meter sand, 5 meter sand layer, and that means the top one would be 2 meters now. Top one would be 2 meters now. Can you see that? And this would be bulk. Gamma bulk was given to you. Gamma sat was given to you. So this would be also gamma sat, but because of capillary zone. Because of capillary zone. So that's also same value of gamma sat. So we have those values 17, 20, 19. 17, 20, 19. Now we need to draw those diagrams again. We need to draw those like diagrams again, but accounting the effect of capillary zone. We had to account the effect of capillary zone. Let's have the reference lines. Let's have those reference lines. These are your reference lines. Okay. These are your reference lines. So first one is there, what you call as total stress diagram. Total stress diagram. Let's go for sigma. Sigma. What is the value here at the top? 17. 17 into 0, that is 0. 17 into 2, that is 34. 34. After that, this would become as a surcharge 34. After that, 34 plus what you call as gamma sat of 20 into 1. So this would be this increase would be the increase would be because of that 20 into 1. This is 20, so final value would be 54. Final value of 54. So this becomes a surcharge for the soil below 54. After that, there's what you call as 54 is constant now. After that, we have gamma sat into 20, gamma sat into 2. So 20 into 2, that's 40. So we have increase of 40. Increase of 40. So final diagram would be 94. Final value of 94. Final value of 94. So 94 becomes a surcharge. 94 kilonewton per meter square becomes a surcharge for the soil, that is the clay below that section. After that, we have 94 plus your gamma sat for the clay into 4 meters. Gamma sat into 4. 19 into 4. So this value would be 19 into 4. 19 into 4. So final value would be somewhere here. So that would be your total stress. So total stress at the bottom is equals to how much? How much is that final value? That final value is actually 170. 170. You can check that. 94, 54, 34, and that is all. And we can show that this is your 0. That's your 17 into 2. After that we have 54. That's because we have 34 plus 20 into 1. After that we have 54 plus 20 into 2. After we have 94 plus 19. We have this 94 plus 19 into 4. 94 plus 19 into 4. 94 plus 19 into 4. That's 170. So that's your total stress. Let's go for the pore water pressure diagram. Pore water pressure diagram. So I would say there is no pore water pressure here. There is no pore water pressure. No water is there, so no pore water pressure. And one more thing is there. What you call as, yeah, I would say at the groundwater table. At the groundwater table, what is the pore water pressure? Pore water pressure at the groundwater table is actually 0. Because if you try to insert that piezometer at the groundwater table, you would see that there is no rise of water in the piezometer. There is no rise of water. There is no rise of water. So H equals to 0. H capillary equals to 0 at that. Yeah, H equals to 0 in that at that point. So your pore water pressure is 0 at that location. 0 at that point. 0. 0 is the stress at that point. 0 pore water pressure. After that, we would say above the groundwater table, there is capillary zone, so we have negative pore water pressure. So we have negative pore water pressure up to the in the capillary zone. So this would be equals to how much? How much is this value? If I substitute the value of gamma W as 10, so we have this 1 meter. We have this 1 meter. So finally, this would be 10 kilonewton per meter square. Can you say that this is your 10 kilonewton per meter square? But this value is negative. And from the side, we will go a linear increase, and slope would be same here. Slope is same because we are having gamma W, that's fixed value. So here we have final value of u at the bottom is equals to how much? From the groundwater table level, that is 2 meters plus 4 meters, so 60. I would say this is your 60 value. Here we have 20, 2 into 10, 20 pore water pressure. Let's go for third one. That's total effective stress. Effective stress is actually difference of the two. Effective stress is the difference of the two. Sigma minus u. Sigma minus u. So initially that is 0. That is 0. After that 34 minus 10. Yeah. 34 minus, let's go for the first case, that's just above that level, just above that reference level, just above that reference level. So initially we have 34. Yeah, let's have that. Let's see that. We have 34 just above that level. 34. So I would write 34 minus, just above that level we are having zero value of pore water pressure. So 34 minus 0, that is 34. And just below that, now cut the section just below that. We're having 34 here, and we're having pore water pressure negative 10. Negative 10. So just below that I would have 34 minus of minus 10. So minus, I would say final value of 44. So increase of that diagram, that's 44. Final value of 44. 44. After that there is, after that all the stuff is easy. I would say here we have final value of 54 minus 0. So 54 minus 0. So that's 54. 54. That's 54. After that we have 94 minus 20. 94 minus 20, that is 74. 74 is there. This is 74. After that, I would write 170 minus 60. 170 minus 60, that's 110. So 110 is there. So final diagram is your effective stress diagram. 110. So that's your, this is all of that problem. Let's go for the third part of the problem. Case number 3. Case number 3. Let's go for the case number 3. Case number 3. So we can have a conclusion here that we already know that because of the capillary zone, your pore water pressure uh, is negative. Pore water pressure is negative, so effective stress increases with respect to the original value. If there was no effect of capillaries, if there was no effect of capillarity, so your sigma minus of minus u, it becomes more. It becomes more. That we can see in the diagram that there is increase of that uh, effective stress at that same location where your capillary zone effect is there. You can see that because of this effect, because pore water pressure is negative, so effective stress increases. Let's go for the third case of the problem. So all the cases are derived from the initial case. All the cases are derived from the initial case. Let's talk about the third case. Let's talk about the third case that's given. Third case is there, and it says that. So case number 3 we can write. Case number 3. What the problem is saying? Case number 3 is saying we have 4 meter deep sand layer. Deep sand layer of gamma bulk equals to 20. Place it on the ground level. Place it on ground level or surface. We can say at the ground level, at the surface, ground level. So we need to get effective stress at the center of clay layer. At the center of clay layer. Get the effective stress at the center of clay layer. So there is a clay layer. So we have this clay layer here. 4 meter clay layer is 4 meter clay layer is there. So we have to get that effective stress at the center of that layer. So somewhere here, at the center of that layer. But what is the condition? Because we have added how much? We have added 4 meter sand layer of gamma bulk. Gamma bulk equals to 20. So this would act as a surcharge now. I would say this would act as a surcharge for your clay layer. For your clay layer, center of the clay layer, this would act as a surcharge. We have already seen that. If we have all those stress diagrams, I would say your stress above that level becomes as a surcharge for clay below that. Your stress above at this level becomes a surcharge for all the clay layer below that. Your stress at this location becomes a surcharge for all that stuff below that. Can we say that? So similarly, we would say this 4 meter deep sand layer can be converted as a surcharge for the clay layer, such that I can calculate finally what is the stress at the center of that clay layer. Now it is having subparts, so it's having two more parts, two more subparts. So part number 1 is there. We need to calculate the stress, okay, but calculate immediately after that placement of that 4 meter sand layer. Immediately after fill has been placed. After fill of 4 meter sand layer is placed. Fill has been placed. Okay. So we have the concept that when there is any load applied on the soil mass, any surcharge. So at the immediate time, what is happening there? If you assume that soil is laterally confined, when you assume that soil is laterally confined, lateral strain for the soil is 0. That means no stress taken by solids, only the extra stress taken by because of pore water pressure. So excess pore water pressure gets developed, that's equals to surcharge. So that's the concept we had to use for the immediate concept, immediate case. So let's go for that. So we are going to place that surcharge of, so we can convert this 4-meter sand layer. We can convert this 4-meter sand layer as a surcharge of Q equals to this is a stress kilonewton per meter square. How can you convert that? If you have this 20 kilonewton per meter cube for 4 meters, so I would write this is your stress of 20 kilonewton per meter cube into 4 meters. That's 80 kilonewton per meter square acting for that particular cross section area of a meter square. So that's your 80 kilonewton per meter square stress is acting on that. So let's try to get those. Let's try to place that stress surcharge of 80 kilonewton per meter square at the ground level. So this is your Q equals to 80 kilonewton per meter square. Okay, 80 kilonewton per meter square. Now because of that, we had to change the diagrams now. Your diagrams would get changed. Can we say that your diagrams would get changed? I would say your diagrams are going to get changed. Your diagrams are going to get changed now. Your diagrams are going to get changed. Let's say that we are going to change the diagrams now, and we don't have to calculate at all the locations. We have only we can directly calculate only at the critical location. If we play very smartly, we can calculate at the critical location only. That's at the center of the clay layer. We only need to calculate just the effective stress, just the effective stress. So if I try to calculate directly what is the effective stress at the mid span, at the mid part, at that time I would say your effective stress would be actually that Q plus gamma bulk into what you call as your groundwater table is somewhere here. So this is 3 meters. So I would write gamma bulk into 3 plus gamma sat into 2 minus gamma W into 2. After that we would write we have this clay layer of 19. So after that gamma sat of clay into 2 minus gamma W into 2. After that I have to add one more data. That's because of what you call as, yeah, that's the surcharge. So your pore water pressure also increases. So your U value also increases. Your value of U also increases by that same amount of Q. So your value of U also increases by that same value of Q. So but I had to subtract that. Because this is because the equation is actually sigma minus U. So my U value is actually, from this calculation I would say my U value would be 2 gamma W. My U value would be 2 gamma W, and one more 2 gamma W is there, and there is one more value of Q. So finally my sigma would, your effective stress at the midspan would, I think, would remain same. Your effective stress at the midspan would remain, I think, same. I had to check that now. I had to check that for the immediate condition. Let us now check. I would say my solution would be directly. If I try to calculate directly, it's all about the concepts and that practice. I would say your stress would be as per the initial value sigma at the midspan of that clay layer, at the mid I would say center of the clay layer. The initial value we got at the clay layer midspan, this would be same effective stress at this condition also for the immediate condition. That is the case number 1. Immediately after the fill has been placed, we need to solve now. I would say your solution would be same value. Now let's try to check that. You can verify that at final time. So let's try to go for the solution. Let's try to go for the solution. I would say we had to calculate stresses at this location. Can you tell me what is the effective stress at this location? So by using the concept that we are solving for the immediate time, that is at time t equals to 0. At that time our concept is that your effective stress, that is your pore water pressure is getting developed extra, that's excess pore water pressure develops, that is equals to how much? That's equals to Q. And your total stress would be definitely going to increase. That's going to definitely increase, because that is the definition that what is the total load above divided by area of the cross section. If you have this Q, that is definitely going to be accounted in the value of sigma. So if I say that what is the sigma at the location of that midspan, sigma at the center of C, if I write sigma C, so sigma C would be actually your value of Q plus gamma bulk for the 3 meters, gamma bulk for 3 meters, okay, gamma bulk for 3 meters. After that we have gamma sat for 2 meters plus gamma sat for 2 meters. After that we have this one more data, that's gamma sat for the clay for 2 meters plus gamma sat for the clay for the 2 meters. This one is for sand, this one is for clay for the 2 meters. If I try to substitute those values, so your value of Q is 80 kilonewton per meter square. Your bulk unit weight of the soil, dry sand is 17, and we have 3 meters of that layer plus gamma sat of the gamma sat for the sand, that is 20 into 2 plus gamma sat for the clay, that's 19 into 2, gamma sat into 2, 19 into 2. So final value of sigma C is equals to how much? 209 kilonewton per meter square. At that same location, at the mid span of that, at the center of that clay layer, I would say, at the center of that clay layer. That's why I have written here C, at the center of that clay layer. Now for the pore water pressure calculations, let's go for pore water pressure at that what you call as C, at that C center. So I would say uh, let's ignore that surcharge first. Let's ignore the surcharge. I would say there is no water in this part. In this part there is no water, so I would write 0 plus here we have gamma W. Here we have gamma W because we are having water table here. So I would write how much water table we have, how much height of that we can finally write. How much is this height? Because water table is here, so this would be all hydrostatic pressure up to this level. Hydrostatic pressure. So that's actually 4 meters. 2 plus 2 meters into gamma W. So that's 4 gamma W. And after that, this is the static pore water pressure, because this is hydrostatic pore water pressure. This part is hydrostatic pore water pressure, that is static pore water pressure. Now we need to add one more data. That is the excess pore water pressure. What is the excess pore water pressure? So that's actually equals to Q. Your Q value is actually 80. So final value of pore water pressure is how much? 40 plus 80, that is 120 kilonewton per meter square. So do we got it? We have the concept that at the immediate time, your all the surcharge is taken by your pore water pressure. Your pore water pressure that's trying to resist the change. Your pore water is trying to resist the change. So finally, your extra stress that gets developed in the pore water is actually equals to the surcharge itself. Surcharge itself. So stress in the soil solid is at the immediate time is equals to 0 because of that increase, but after some time there would be definitely those solid is going to take the stresses. So for the immediate condition, so this is your sigma C, this is your UC. So finally your effective stress would be, your effective stress at that center of the clay layer would be sigma C minus UC. So that's 209 minus 120. So that's how much is that? 89 kilonewton per meter square. And if you try to compare that with the initial case, initially how was the distribution of that? Let me check there. How was the distribution? Yeah, it was in some sort of that we're having a diagram of that total effective stress in this way, that we're having 51. After that we're having 71. After that final value of 107. So we're having 107 at the end of the clay layer, and at the start of the clay layer we're having 71. This was your 4 meters, and at the midspan, at the center of the clay layer, what is the value? We can check by the linear interpolation. So here we can say what is the value. That would be 71 plus 107 minus 71 for the 4 meters, but I need for the 2 meters. So you can check that final value would be 89 also. So your effective stress does not change. That means we can conclude here. These things we already know. We have talked about that. So your effective stress does not change. Does not change immediately. Does not change immediately by placing surcharge. Because of surcharge. Because of surcharge. That's actually because your increase of total stress is taken by increase of pore water pressure. So we have that concept that sigma equals to sigma dash plus u. We have that section. We have those grains. We have those summation of ni, summation of all those ni, and we have that pore water pressure. So we have that summation of fy goes to 0. Your external load was surcharge. Your external load of surcharge was there, q, and there was soil also, similar to that of original condition. There was some soil, there was some surcharge also. So weight of the soil plus surcharge equals to some value of total P, and divided by the area of cross section. That will give me your value of sigma, and that is resisted by pore water pressure into area of the pores, and your effective stress into that area of the total area of the cross section. Now, I would say your total stress got increased by value of Q, and that is balanced by the increase of pore water pressure equals to excess pore water pressure, that was also equals to Q. So the increase of pore water pressure was also equals to Q, such that your change in effective stress was 0. So change in effective stress was 0. So finally I would write, for the immediate condition, your change in effective stress is equals to 0. If you try to compare the values of sigma c initially, so let me show that. If you try to compare this value of 209, that is the total stress at that mid center of that clay layer, that is 209. If you try to compare it with the original condition, you would see that the initial value should be equals to 209 minus that Q value, that is 80. So initial value, you would see that this should be 129. You can check that, you can verify that. And your pore water pressure initially should have been 120 minus 80, that should be 40. You can check that also from the initial condition, that pore water pressure at the center of the clay should be 40 kilonewton per meter square, such that final value of sigma bar is not going to change, because the increase of sigma is balanced by the increase of u. Increase of sigma is balanced by this increase of u. So because there is increase of uh, what you call as sigma, there is again increase of what you call as u, such that both are same, and there is no increase in the effective stress for the immediate condition. So let's go for the case 2 of that same part, same problem. Case number 2, that means after a long time that fill has been placed. After a long time fill has been placed. After a long time fill has been placed. Let's go for the part 2. Case B, after a long time, we're coming to the soil after a long time. We want to calculate the effective stress at that center of the clay layer, but after a long time, this surcharge has been placed. Surcharge of 80 kilonewton per meter square has been placed. So let's try to remove all that stuff. Let's try to remove all that stuff. Okay. So we have the second part, that's after a long time, after a long time, after a long time. So this is your center of the clay layer, and at that location, can you tell me what is the what is the total stress? So that would be same. Would that be same as that of a previous case, because it's not going to change. That's your 80 plus gamma bulk into 3 plus gamma sat, this is your water table, gamma sat into 2 meters plus gamma sat for the clay, that's 19 into 2, 19 into 2 for the center of the clay. That would be same as that of a previous case. That would be how much? 209. Yeah, 209 kilonewton per meter square. That would be same as that of a previous case. And if we talk about that pore water pressure, so the pore water pressure at that center of the clay would be actual original value of the pore water pressure. It would be original, because what's happening here? Uh, because the water is trying to resist the change, the pressure gradient that got developed. Let's have this little bit of concept. Because of the pressure gradient that got developed, because of the pressure gradient that got developed at the immediate condition, because of excess pore water pressure, pore water pressure, there is flow of water towards the drainage. What you call as, there is flow of pore water towards the drainage phase. such that I want that your excess pore water in the soil, excess pore water pressure in the soil should be 0. So such that for getting this condition, I want that there should not be any excess pore water pressure in the soil. So for that, I had to drain the soil. Soil should be in the drain condition, or I would say there should be the dissipation of pore water pressure. There should be dissipation of pore water pressure. And finally, when there is loss of that water, so all of that increase of that surcharge, that is taken by now that effective stress. That should be taken by effective stress now. That we need to check now. So I would write that your effective stress, your pore water pressure now would be equals to the original value we have. Original value. We don't have to add the value of Q. We don't have to add the value of excess pore water pressure. Let's see that what is the total value here. So we have the water level. This is your water table. So at this location we are having hydrostatic static pore water pressure only. So we can write this is your 4 gamma W. So that's your 4 into 10 plus U excess. Your excess pore water pressure is 0 at after a long time. That's because of dissipation. Because of dissipation of pore water pressure. Excess pore water pressure. Okay. So finally, same value as that of original value, 40 kilonewton per meter square. And that means your effective stress would be sigma C minus UC at the center of the clay. At the center of the clay. So that's 209 minus 40, that's 169 kilonewton per meter square. 169 kilonewton per meter square. And if I try to compare it with the original case, if I try to compare it with the original case, your original value was 89. That was 89 at the center of the clay. That was some value of 89 here. 89 kilonewton per meter square sigma. So there is increase, I would say there is increase of that effective stress by how much value? So your increase, I would say change in the effective stress is actually that is increase of 80 kilonewton per meter square. That is equals to surcharge. That's equals to surcharge. So all of that surcharge is now taken by the soil solids. That is the contact forces between the soil solids, such that you got this increase of 80 kilonewton per meter square. Okay. So let's see the equation. We have sigma equals to sigma bar plus pore water pressure. So at that interface, at that section, you are adding that surcharge, and there is some soil also. So I would say your total stress is actually that weight of the soil. Because of the soil we are having some stress sigma 1, and we are having some sigma because of the surcharge equals to Q. So final value of Q was given to final value of sigma was 209 kilonewton per meter square, and that should be equals to your initial value of U is your value of U is going to remain same as that of initial case, same value of initial case. That means the extra part of the Q, it has to be now taken by the soil solids. It is now has to be taken by the soil solids. So if there was initially your effective stress of sigma naught, original value, that means it has to be increased by value of Q such that its final value equals to how much? That's 169. Initially it was 89, we had to add value of 80 such that it becomes 169. That was all about that problem. I hope you have enjoyed that stuff for your effective stress calculations. Thank you for watching. I would say thank you for watching.